Okay. Okay, guys, let's continue to the lecture. Okay. Let me go to my notes. Okay, so let's start our lecture. So, okay. So let me go to our lecture. Yes. So today's lecture, our focus how to find electric field. So for a point particle, I'll try to simplify this physics a little bit difficult. So for electric field, so I use a notation for electric field this. So today's lecture, I'll focus more on electric field. So how can I find electric field? First of all, before that, let me discuss about force. Force, I use a notation force like this. And then if you have two charges, Q1 and Q2, I'll try to simplify and then separate by distance R. So the force that the two charges experience is going to be K times Q1 times Q2 over R squared, where K is a constant, okay? K is just 9 times 10 raised to 9 Newton meter squared, Coulomb squared. Q1 is charge 1, Q2 is charge 2, R is the distance between the two, okay? Now, electric field by definition is just, electric field by definition from now on is just force divided by charge. So it's a vector quantity, and or in other words, force is nothing else but electric field times charge. Okay. Now I'm done. So today's lecture gonna be electric field for a point particle. So electric field point charge. So how can I find electric field for a point charge? Okay. So it's a little bit difficult concept. So try to understand. So electric field for a point particle is given by K times Q over R squared. You need only one charge for electric field, only one charge. So for instance, if I have a Q1 charge, it creates what? Electric field around its vicinity. It creates electric field everywhere. But if I ask you, how can I find the electric field at point P, okay, where R is the distance from Q to P, is going to be given by K times Q over R squared, where K is a constant, it's a Coulomb constant, Q is the charge, R is the distance from the charge to the point P. P is a space. There is nothing on a P side, it's just a space. So if I ask you electric field, the magnitude is going to be KQ over R squared, where K is a constant, which is given by this, Q is the charge, R is the distance from the charge to the point P, okay? So, but the problem with electric field is not simple because electric field is a vector quantity. So electric field, so the electric field is a vector quantity, is a vector quantity. Means it has what? It has magnitude and what? It has magnitude, it has magnitude, it has magnitude and direction, okay? Direction. It has magnitude and direction, okay? How can I find the direction? Okay, to find the direction of my electric field use positive test. Okay. And then the direction of my positive test charge is the direction of electric field. Okay, this is so electric field is a tricky concept because it has magnitude and direction. To find the direction, use positive test charge, and the direction of the positive test charge is the direction of the electric field. Let me give you one simple example, okay? In today's example, for example, if I have a Q1, just I have a charge which is one coulomb, and that charge is just, it's one, so P is space, and R is just 1 meter, okay? So P is space, there is nothing here. I want to find the electric field at 1 meter, okay? You can find electric field everywhere, but I'm interested only in one direction, and a P at P. So how can I find electric field, okay? So to find electric field, you see, the magnitude is simple. It's going to be K times Q1 over R squared. K is 9 times 10 raised to 9 Newton meter squared, coulomb squared. Q1 is just 1 coulomb over the distance from Q1 to P is just 1 meter squared, okay? So meter squared cancel meter squared, coulomb cancel coulomb, so 9 times 10 raised to 9 Newton per coulomb. But how can I find the direction? To find the direction, put your positive test charge at P, because I'm asking you to find electric field at P. Put your positive test charge. Now your positive test charge is gonna repel because Q1 is positive. Your positive test charge is positive. Your positive test charge is gonna repelled by Q1 because like charge repel each other. Then my electric field is towards the right because the direction of your positive test charge gonna pushed by Q1. So the direction of the electric field is the direction of your positive test charge. Since your positive test charge is pushed by Q1, and electric field will go towards the right. Then you have to use X. X is a unit vector. It tells you that the electric field is in a positive X-axis. Now you find the direction and you find the magnitude, okay? If you don't understand this, let me give you another example. Q1 is just -1 coulomb. Now, I want to find the electric field at P, where P is 1 meter far from Q1. P is space. There is nothing there, okay? So, okay, the electric field. So first you have to find the direction, use your positive test charge, because your positive test charge is going to attract it by Q1, because unlike charge attract each other, because Q1 is negative, your positive test charge is positive. So that means your positive test charge is going to be attracted to Q1. So E1 going to be towards the left, okay? Because your positive test charge will go towards Q1 because it's going to be attracted. The direction of the positive test charge is the direction of electric field. Then the electric field, you know that now is a negative X direction. To find the magnitude, just simply plug Q1 over R squared. Don't put any negative number because the charge is already, the direction is already taken care of. Even if Q1 is negative, don't put. So it's already taken care of. So K is 9 times 10 raised to Newton meter squared, coulomb squared. K1 is just 1 coulomb, and then the distance R is just 1 meter squared. So meter squared cancel meter squared, coulomb cancel coulomb. So your electric field will be -9 times 10 raised to 9, okay, Newton per coulomb in negative axis direction, because your positive test charge is going to be attracted towards Q1. So the direction of the positive test charge is the direction of the electric field. Done. Okay. So this is how you find the electric field. Okay. But what about now? My question is, what about if you have many charges? Like I have Q1, Q2, Q3. And then P is just a space, there is nothing. And this is R1, this is R2, this is R3. So Q1 is going to create electric field everywhere. Q2 gonna create electric field everywhere. Q3 gonna create electric field everywhere. So Q1 gonna create also electric field at P, at point P in space. Q2 gonna create electric field at P. Q3 also gonna create electric field at P. Okay. So each charge gonna. So how can I find the electric field? So from your superposition principle, the net electric field at point P is the electric field because of Q1 plus the electric field because of Q2 plus electric field because of Q3. It's a vector quantity, okay? So that's a net vector, but this is a vector. Be careful when you add vector, care must be taken because that vector has magnitude and direction, okay? Now, let me give you one example, okay? To make your life simple, let me give you one positive one charge, and then I have another positive one charge. And so I want to get in the middle. I want to find the electric field in the middle. So in the middle, P is just nothing. It's just a space. So in the middle, what's going to be the electric field? Okay, guys, what can I do? You know, first, be careful. You have to find the direction of the electric field because I have two charges. Each charge creates electric field at point P. So I have two electric field. One's from Q1, the other one's from Q2. Okay. So to find the direction, use positive test charge. Okay. Now your positive test charge. Now Q1 doesn't like you because you are positive. Q1 is positive. It's going to push you towards the right. So Q1, my positive test charge goes to the right. Why? Because Q1 going to push it towards the right. Oh, then the electric field from Q1 is towards the right. Q2 is positive. It's going to push your positive test charge towards the left. Okay. So Q is a positive. One column is positive. So your positive charge, one column, going to push your positive test charge towards the left. Okay. Because your positive test charge is positive. Q2 is positive. Okay. So Q2 going to push your positive test charge towards the left. Oh, the electric field from Q2 is towards the left. Okay. So, and then to find the magnitude of E1, you know that it's going to be K times Q1 over R squared. K is just 9 times 10 raised to 9 Newton meter squared, column squared. Q1 is just one column. R is the distance from the charge Q1 to the point P, which is 1 meter, and then squared. And then you get 9 times 10 raised to 9 Newton per column, and a positive X direction. That's the electric field. And why is positive? Because E1 is positive because I showed you here. And E2 is K times Q2 over R squared. K is 9 times 10 raised to 9 Newton meter squared, column squared. Q2 is just one column. And then Q2 is far from P by how much? By 1 meter. Okay. So this is going to be negative. Why negative? Because E2 is towards the left, negative 9 meter squared, cancel meter squared, column, cancel column. So 9 times 10 raised to 9 Newton per column in negative X direction. Okay. And then from superposition principle, the net electric field at point P is just electric field because of Q1 plus electric field because of Q2. Electric field because of Q1 is 9 times 10 raised to 9 Newton per column in X direction. And electric field from Q2 is just negative because it's negative in negative X direction. So the net electric field is 0. Means you don't have any electric field at point P because they're going to cancel each other. Okay. That's it. Now, let me give you another very good example. Perhaps this might be the good example for point particle. Now, let me have another charge Q1, which is one column. And I have another Q2, which is negative one column. And Q1 is 1 meter apart from Q2. And then I want to find a space. P is a space, there is nothing there. And P is 1 meter away from Q2. I want to find electric field. Find electric field at P. So I want to find the electric field at P. What can I do? Yes, use always your positive test charge. Okay. Now ask Q1 gonna push you because like charge repel each other. So Q1 gonna push you. My positive test charge gonna be pushed by Q1 towards the right. Oh, electric field from Q1 is positive X-axis. My positive test charge is positive, so Q2 is negative. So Q2 gonna attract my positive test charge. Oh, electric field from Q2 is towards the negative X-axis. Okay. I'm done. Now the direction is taken care of. Now you don't need to put negative number in your calculation. Don't make any mistake, okay? So E1 is just electric field because of charge 1. It's going to be K times Q1 over R squared. K is 9 times 10 raised to 9 Newton meter squared, column squared. Q1 is just one column. And Q1 is how much far from point P? Look, 1 meter plus 1 meter. 2 meter squared. It's going to be 9 over 4 times 10 raised to 9 Newton per column. Meter squared, column cancel column. And a positive x-axis, because you're already taking care of the sign of A1 already. Is in a positive x direction. For Q2, it's going to be K times Q2 over R squared. K is just, it's a Coulomb constant. It's from experiment. Don't worry about that. Q2 is negative, but I don't put negative number because I already taking care of the sign. And Q2 is how much far from P? It's just 1 meter far. Yes? And then do the algebra, meter square, column, cancel column. It's going to be negative 9 times 10 raised to 9 Newton per column. Why negative? Because E2 is towards the left. You see, E2 is towards the left already, taken care of. So E1 is positive, E2 is negative because already taking care of the sign. You don't put any negative number, even if Q2 is negative, don't put that negative because already the sign is taken care of. So the net electric field is going to be E1 plus what? Plus E2, yes? E1 is just 9 over 4 times 10 raised to 9 Newton per column in a positive x direction. E2 is 9 times 10 raised to 9 Newton per column in negative x direction. So if you add this, it's going to be 4 is common, 9 minus 36 times 10 raised to 9 Newton per column. In x direction, this is negative 27 over 4 times 10 raised to 9 Newton per column in x direction. The net electric field is negative because E2 is extremely big than E2. E2 is extremely big than E1. That's why, because E2 is close to Q from 2P. That's why the net electric field is towards the left, okay? This is how you find electric field. But life is simple. Guys, life is simple because everything is in one dimension. But this is not the case. This is not the case. Life gonna be complicated. So first of all, we are dealing only in a point particle. So life is simple. Second, also, so far we are dealing only to find electric field in either an x direction or y direction. But sometimes the electric field can have two components, x and y component. How can we address? For instance, let me give you one example. Consider two charges. Okay, two charges. Charges Q1 is equal to Q2 is equal to 2.9 times 10 raised to negative 6 coulomb are placed at two corners of square. Okay, of 0.5 meter. Find the electric field at point B. So far I have Q2, which is 2.9 times 10 raised to negative 6 coulomb, the int of charges column, don't forget. And then I have Q1, 2.9 times 10 raised to negative 6 coulomb. And this is 0.5 meter. And then I want to find, this is space. B is just a space. There's nothing. And I want to find the electric field here. Oh, because of Pythagoras theorem, okay, this is just how much? It says 0.5 square root of 2 meter. This is from Pythagoras theorem. The distance from here to here is 0.5 times square root of 2 meter. And then I want to find the electric field. What can I do, guys? How can I find the electric field? Before you even start, you have to find the direction of the electric field. So we have two charges. Each charge creates electric field at point B. To find the direction of the electric field from the two charge, put positive test charge at B. Okay, I bring my positive test charge. Oh, because my positive test charge is positive, look, Q2 gonna push my positive test charge towards the right. Oh, the electric field from Q2 is a positive x-axis. But Q1, look, is positive. It's gonna also push my positive test charge this direction. Okay, so the electric field from Q1 is like this. And then because of your geometry courses, this is just 45 degrees because this is a square. So this is 45, this is 45, and this is 45. So let me repeat one more time. Since Q is positive test charge, Q is gonna push my positive test charge towards the right, okay? Q1 is also positive, my positive test charge is positive, so Q1 gonna push my positive test charge like this, or the electric field for E1 is this direction, and this angle is 45 degrees. Now I have a problem. First, what you have to do is find the magnitude of E1, find the magnitude of E2, okay? So E1 is electric field from Q1. It's going to be K times Q1 over R squared, okay? K is just 9 times 10 raised to 9 Newton meter squared, Coulomb squared. Q1 is just 2.9 times 10 raised to negative 6 Coulomb. The distance Q1 is how much far from point B? It's just 0.5 times square root of 2 meter squared. Meter squared cancel meter squared, Coulomb cancel Coulomb. So do the algebra. It's going to be 5.21 times 10 raised to 4 Newton per Coulomb. There is no problem here, but electric field now I don't have any direction because the electric field for E1, it has X component and Y component. Just leave it now. Leave it. For electric field for the charge 2 is just K times Q2 over R squared. K is just 9 times 10 raised to 9 Newton meter squared, Coulomb squared. Charge 2 is 2.9 times 10 raised to negative 6 Coulomb. And the distance from Q2 to B, it's just only 0.5 meter. From here to here is 0.5 meter. And then meter square cancel meter square, Coulomb cancel Coulomb. So the algebra on 1.04 times 1.04. Let me make it like simple. 0.4 times 10 raised to 5 Newton per Coulomb. Now, I have a problem. Because E1 and E2, we cannot add directly. So the net electric field in it is just, you know that, is equal to E1 plus E2. But you cannot add this vector together because they are not in the same direction. So you have to remember your mechanics class. So from your mechanics class, you know that you cannot add this vector directly. How can we add these vectors? First, you have to get the X and Y component of each vector. First, get the X. Add the X component of each vector together. Add the Y component of each vector. Let me show you. So you cannot directly add like number. So you have to add vectorially. So you have to get the X component of each vector. For example, E1 has how many components? Look, E1 has X and Y component. So E1 has X. So E1, look, E1 has a X component and Y component, okay? One. So it has X and Y component. To find the X component, yes, it's going to be E1 times what? Cosine of 45 degree. That we learned last time, but E1 is already calculated. It's going to be 5.21 times 10 raised to 4 Newton per Coulomb. Cosine of 45 is just 0.7 around that. And the algebra, you get 3.68 times 10 raised to 4 Newton per Coulomb. And this is E1Y from your last time we learned E1Y is E1 times sine of 45 degree. So E1 is 5.21 times 10 raised to 4 Newton per Coulomb times sine of 45. Do the algebra. Okay. So it's going to be 3.68 times 10 raised to 4 Newton per Coulomb because sine of 45 and cosine of 45 are the same, 0.7 something. So fortunately, the X and Y component are equal. Okay. But for E2 has only X component, you know. A2 has only X component. Look, A2 has only X component, so we don't care. So, and that X component is already, we found it, 10⁻⁵ Newton per Coulomb, okay? And A2 doesn't have any Y component, okay? So first, to add this vector, you have to find the X and Y component of each vector. Then add the X component of each vector together. Okay, so add 3.68 times 10⁻⁴ Newton per Coulomb plus 1.04 times 10⁵ Newton per Coulomb. Add the X component of vector E1, add the X component of E2, and then that's how you find it. Do the algebra. If you see any type of error, fix it by yourself. Add the Y component of each vector, E1y plus E2y. But E2y is just 0. This is 0 because we don't have any X component. Just only the Y component is already taken care of here. 3.68 times 10⁴ Newton per Coulomb. That's it. Now, so you have to add the X component of each vector, the Y component of each vector. Then the magnitude, the magnitude is equal to A net X squared plus A net Y squared, okay? And then the A net X is 1.41 times 10⁵ Newton per Coulomb squared plus 3.68 times 10⁴ Newton per Coulomb squared, okay? Do the algebra. What you get is 1.46 times 10⁵ Newton per Coulomb. That is the electric field, the magnitude, but electric field is a vector quantity. It has magnitude and direction. To find the direction, you have to find the angle, or you can just put it in a vector form, this in X plus this in Y, or you can just find the angle. To find the angle, tan inverse of A net Y over A net X, okay? So, and then tan inverse of, make sure your calculator, you have to have your calculator at hand. You should do it by yourself. If you see a typo error, write it in a comment section. And then the net vector going to be 40.6 degree, okay? That's the angle. So I found the direction, right? The theta is the direction. I found the magnitude. So this is how you find the electric field. So if you have in two components, okay? Okay, I'll not repeat. I'll not go to that direction. I'm done. Now let me go to next electric field lines. Electric field lines. So I have charge, positive charge Q, and I have negative charge Q. How can I find this is positive Q, this is negative Q? How can I find the electric Q creates what? Electric field in your vicinity. Q1, this charge also, this Q also creates an electric field. It's on its surrounding. So if you bring positive test charge, always to find the electric field direction, use positive test charge. So your positive test charge going to be repelled. Bring positive test charge, it's going to be repelled. Bring another positive charge, it's going to be repelled. If you bring another positive charge, it's going to be attracted because your positive charge, unlike charge attracts each other. If you bring positive charge, it's going to attract. If you bring positive charge, it's going to attract towards minus Q. So the electric field going to be what? So the electric field going to be from plus to minus. Okay. Always when you have electric field, it's go from plus to minus. So the direction of the electric field is from plus to minus. Okay. But let's use this. So electric field, the direction of electric field is from plus to minus. Always you have to use positive test charge to find the direction of the electric field. Okay. Now, I have another question. If I have electric field created somewhere in space, I don't know, it's coming from space. Okay. Since electric field go from plus to minus, don't forget the tail is more positive. This is not, it's not good to say that, but let me say it. Okay. This is more negative. The tail is, because you see electric field goes from plus to minus. Look, that means the tail is all more positive. The arrow is more negative. Okay. Now, let me give you an example. For example, now just I have this. My electric field is 2 Newton per coulomb. Okay, and a positive x-axis. I don't care. Now, if I bring a Q, which is 2 coulomb, okay, find the force. So my electric field force is by definition electric field times charge. Okay. Now, be careful. My electric field is 2 Newton per coulomb. This is the unit of electric field. C is the unit of coulomb. Okay, charge. C is the unit of charge. So the charge is 2 coulomb. Coulomb cancel coulomb. It's going to be 4 Newton. But electric field is a vector quantity. No, force is a vector quantity. So which way is my 2 coulomb goes? Because this is more positive, this is more negative. My 2 coulomb likes to go what? Towards the arrow, because the arrow is negative. Because my 2 coulomb is positive, it doesn't like positive. It goes to the negative. So it goes to the right. Oh, then my force is positive. Okay, it's 4 Newton in a positive x direction, because my charge likes to go to the arrow. Similarly, if I have electric field, like electric field 2 Newton per coulomb in x direction, and if I bring a charge which is minus 2 coulomb, yes, the force is going to be A times Q, and A is 2 Newton per coulomb. The charge is 2 coulomb. It's going to be 4 Newton. But since my charge is negative, this is more positive. This is negative. This is negative. It doesn't like to go to the arrow. It likes to go what? My Q likes to go to the left. Oh, then my force is, so my force is negative 4 Newton in x direction. You see, this is how you find the electric field. Okay, so this is how to find the electric force. So be careful. If you put negative 2 coulomb, it doesn't like to go to the arrow. It likes to go to the tail. So that means the force is towards the left. If you bring positive charge like this, it likes to go to the arrow, because the arrow is more negative. Okay, this is how you find it. But so far, life is simple for you, because I'm dealing electric field. Okay, I'm dealing electric field, I'm dealing with electric field for a point particle. But no, life's not like that. If you have this apple pen is made up of what? If I charge it, like if I rub it, it's going to be charged either positively or negatively. So the charge is distributed uniformly. For example, I cannot use a K electric field is equal to KQ over R squared. You cannot use that. You have to use calculus. So if you have continuous charge distribution, how can you find the magnitude and the direction? To find the direction, use positive test charge. But to find the magnitude, we'll come to the next part. So for today, this much is enough. I think this much is enough.